Oh, and a laser pointer. Ah, no. Right. Should I get started? Ricardo? Yeah. Okay. So firstly, thank you very much for being invited to come to this and tell you all about a couple of things. Today, I'll be talking about this relatively exciting sort of new for gravitational waves, but old for computer scientists kind of topic, which is deep neural networks, machine learning, and specifically for use for gravitational wave detection. I've got third generation there, but I think this applies now as well. So second generation, third generation, space-based. My name is Chris Messenger, and I'm from the University of Glasgow. So, first slide. That's the Russian parliament, that is. What I'm trying to motivate, I would like this to be a discussion. I think it's started to pick up after the first day, lots of questions. There's my sort of final point there, is to please interrupt me with any questions. What I'd like to do is just put up discussion points, but because this is quite a new topic to everybody, me included, I'm going to have to go through the basics of this. I'm sorry if you already are a machine learning expert and deep neural network expert. I will probably, this is going to be very basic. So what I'm going to do is I'm going to give a brief introduction to the topic with no equations. It's going to be very hand-wavy, and then I will move on to discuss recent applications in gravitational wave data analysis, and then move on to talking points and to have a discussion. But as I say, please interrupt me at any point. Well, my aim here for the first half is that you will come away from this having a rough idea of what neural networks are and why they may be useful for various problems, specifically for gravitational waves, and that you would feel confident that you could go away and do this with the existing software that is out there. You don't have to write your own software to do this. It all kind of exists. So, neural networks, basic introduction, and I've this quote has been attributed to me recently because I said it at a workshop recently. I don't know if that's exactly what I said. When you do machine learning, the only thing that learns is the machine, and what I would hope, my hope is that that isn't true in the long term. But in the short term, it would be very good to exploit that information, exploit that fact, if it is a fact, that machines can learn things that humans might not necessarily, it might not be obvious to them. Okay. So what are they for? Straight out of Wikipedia, machine learning is giving computers the ability to learn without being explicitly programmed. So unlike the analogy here is match filtering. I don't know, we've skirted around match filtering a little bit in the last day or so, where you're saying this is exactly what I think I'm looking for. Please ask the data, is this thing in my data? For machine learning, it's a bit more vague, and I'll get to more specific examples of that. The neural networks I'll be talking about today is one particular aspect of machine learning. Machine learning is very broad, got lots and lots of different techniques and ad hoc approaches. This is just one. And the word deep in front of neural networks, neural networks are just, deep neural networks and neural networks are exactly the same. It's just how many layers they have, and there's no sort of threshold where something becomes deep. So people just like to throw the word deep in front of it, but it just means it has a fair amount of layers, and we'll see what layers are in a second. And they're being used for increasing number of applications, and most notably sort of image recognition. This comes up in your everyday life these days when you go and park your car in a car park and you don't have to take a ticket, or you take your ticket and it has your number plate written on it. That always sort of worries me, but there's a camera that has identified your number plate and read it out and turned it into text, and then they know when you're leaving as well. And this is all done through image recognition, a lot of the time using neural networks. There are other machine learning techniques they use. And it's in the sort of it's being used more and more often recently in the last 10 years, most notably because of GPUs, graphical processing units, because the people who code this up, the computer scientists that put all this together, have realized that it's highly parallel, and they can use the speed of GPUs to make things hundreds, thousands of times faster. You can run all of these codes on CPUs if you don't have a GPU, but you'll find it is literally 1,000 times slower than if you just had a really cheap GPU. So that has made a lot of this possible in the last 10 years. And I've put this box here, a black box with an input and an output, and this is referring to my previous statement about the only thing that learns is the machine. Right now, and for all practical purposes, you don't really get to learn what the machine learnt. You just get to treat it as a black box. So you're asking it to do a task for you, and it will do a task very, very well. You put your input data, and you'll get your output data, but you won't really know how it did it. It's quite abstract inside, despite being relatively simple mathematical operations it's doing. But that's something that I'll talk about at the very, very end. So this is my very first level explanation of how I think about how a neural network works, a deep neural network, or just any neural network. This is a game called Bagatelle. My grandma had one of these, but we didn't call it Bagatelle, and it wasn't as fancy as this. People are happy with what this is, right? You have like these marbles or balls, and you will fire them up the side here, and you get to choose how fast you fire them, and then they land in these pins, in these sort of buckets made of pins, and you get different amount of points for each of these things. I think it's got lots of different names. When I searched on the internet and typed in my grandma's pin board or something, it came up as Bagatelle is the word. So yeah, it's like pinball. It's like pinball. Oh, it's probably got, yeah. So imagine a situation where you were free to place these pins anywhere you liked. And imagine a situation where you had loads of these balls, and they all had different properties. Say they had 3 or 4 different let's say they all had different masses, right? But there was only 3 different types of mass. There was heavy, medium, and light, right? And they're all the same size. And you get to throw them up the side here. What you want, the aim of the neural network, the aim of the analogy here, is that you get to put these pins such that whenever you fire a light one, it falls into the light box. And whenever fire a medium one, it falls into the medium box, and the heavy one into a medium box. And you get to move these pins around. And you do this by trial and error, right? You'll fire one up. You'll fire a few of them up. You'll see where they land, and then you'll move the pins around. And you'll do it. It's obviously very, very hard to do in this particular bad example, but that's the idea. You're trying to move around the internal workings such that it filters the result into the classifications that you want. And so jumping to the very end point of this, for gravitational wave analysis, you can imagine this as we put data into this black box, data from the gravitational wave detectors, and we want it to tell us at the very end, after it's worked out the internal workings, whether or not there is a signal that I've just injected into the data, or whether it was just noise. I want it to be able to tell me, oh, this second of data you gave me contains a gravitational wave signal, or this second contains an artificial detector glitch or something. So that's the idea, and I hope that's got a sort of starting point for you to latch on to what I'm going to be talking about next. So when you get started with machine learning and neural networks, one of the first things you come across is this thing called the MNIST dataset. I can't honestly remember what MNIST stands for. I've used it a lot now, but I've never actually said what what the acronym is for. What it represents is a set of 60,000 images of these things, handwritten digits. So they've got people to write at some point loads and loads of these digits, 0 to 9, so 10 digits. And they're all in different people's handwriting, and there's 60,000 of them, and then there's another 10,000 as a separate set. And they're all made in images of 28 by 28 pixels as well. So it's a sort of well-formatted data set. And they use this as a challenge in computer science to say, how good is your machine learning algorithm? How well can you identify these 10,000 test data sets will give you the 60,000 to train your algorithm on. There's confusion in the room. If you've got a question, please interrupt me. And it's been going over the last 10, 15 years, this challenge, and up till now, the best algorithm is what's known as a convolutional neural network, a deep neural network using convolutional techniques, which again I'll talk about in a minute. And it gets down to a 0.21% error in identifying handwriting. When I say identifying, it's not identifying the person, it's giving it one of these little squares and saying that number is a 3, that number is a 1, that number is a 5. Right? Yep, yeah. So you show it this 60,000. You show the machine 60,000 examples from loads of different people, and then you say, "I've trained my network. Give me the data to do my the actual result on now." And then they find that the best one these days gets 0.21% error, so misidentifies a very small fraction of these. I don't know how many people. It's a lot of people. Each of the digits, I think, is from a different person. I could be. Yeah. I know. Yeah. 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 Well, when you look at I've seen some of the individual ones that are misidentified, and it's when somebody's written a 1 and it looks a lot like a 7, right? So there's human error here in making the data set, right? I know, but it will be. Oh well, other algorithms. Yeah, you've got more data. Yeah. No. No. Yeah. Yep. So that's exactly right. There's no templates. You don't have a model. What you do is show it things lots of times, and it learns. But we will go through how it learns. Yes, the word there is supervised. So this is supervised learning, where the training data, you have the data and you have a label. And the labels in this case are the actual numbers, 0 to 9. And you keep showing it, and you keep saying, when you start training, you give it the 60,000, and it gets 10% correct, because that's random chance of get out of 10 numbers. But because of the pin thing, and it can rework its internal workings, it starts changing those such that you get a better percentage, and it keeps changing. until it's converged on the best it can get with the training data, and then you say, I'll put my 10,000 through and see what the final number is, how good it really is. It does a thing called stochastic gradient descent, where it is random in a sense, but it's random like a Monte Carlo is random. It's trying to find the right set of weights, the right set of pins, to get the best answer out. You have that free choice. You have a choice of what's called a cost function. But we'll get to this, right? These are all great questions. Go on. Oh yeah, yeah. Yeah. Exactly, yeah. Yeah, but that's correct. But you know that. I mean, you want to train something on the thing it's going to then see. One thing you can do is well, no, I won't go into that, but you're quite right. You want to train it on the things you expect it to see. You can't then show this pictures of cats and expect it to identify a cat, right? You can't show it the same. What your analogy was far better of showing it adult handwriting or kids' handwriting. It won't do as well. That's quite right. So it's your responsibility to train your machine, basically. Okay, let's start with an incredibly basic network, right? This has got 3 layers, but there's only really one important layer because one layer you have sort of free choice over. This input layer is your images. So with regards to those 60,000 images, each one of these pink blobs would represent one of those images. 60,000 of these going down. This next layer is what's called a hidden layer. Well, we're going to call it a hidden layer. There are different types of layers I could have put in here, but we're going to talk about a hidden layer first. And you notice this has another number of blobs. It's different to this number of blobs. You can have any number you choose. You get to choose. Each one of these blobs is called a neuron or a perceptron. I'm going to use neuron. And each one of these neurons performs an operation, a mathematical operation on the input. The output layer here is, imagine I was trying to classify whether there was a gravitational wave in my data or there wasn't a gravitational wave. Or let's just stick with images. If I just trained this on images of cats and dogs, then these 2 outputs represent cat and dog. There's 2 classes of things I'm trying to identify. If I was trying to identify the mass of my cat, that's a rather stupid analogy. Imagine I just showed it cats of different masses, and I told it, every time I showed it a picture of a cat, I told you its weight. Then I would just have one of these nodes here because there's only one number I'm interested in, which is the weight of the cat. I want it to tell me what that is. So you can do classification, where you're asking it to classify things, or you can do parameter estimation. You can ask it to identify parameters, to estimate parameters of your system. But let's just think about classification to start with, and there would be cat and dog. Notice that there is a line from every single one of the nodes going to every single one of the nodes in the next layer, and that means it's fully connected. I have never experimented with not fully connected, but it's entirely possible that you say, I'm not going to have fully connected, I'm going to have only some of these go to the nodes. And I don't know why you would choose that, but you can do that. So there's lots of ad hoc flexibility here, but just imagine every single one of these inputs goes into every one of these and then goes out to the next one. I'll show this image again a couple of times so that you're familiar with what's going to be going on at each of these stages. So your input data format, again, with all of this, you've got so much free choice. It can be whatever you like. So typically, input has been in the form of 2D images because all of this has been driven by image recognition. So a lot of it is cats and dogs. But it doesn't have to be. You could use color images. So these are color images, and they're actually, you've got a red, green, and a blue. So it's actually 3 images on top of each other, a sort of cube of information, so 3D information. And people even use video. So you have, if you had color video, you have a 4-dimensional data set that you're showing. Or you could go the other way and just use 1-dimensional data. You don't have to use images. You can just use time series, which is what I'm going to talk about for gravitational waves in a minute. And it doesn't have to be time series. It could be frequency series as well. And what the computer scientists are very keen on, they stress very heavily, is that you have to precondition your data. The machine does not like just any old data coming in. It likes everything to be uniform. If you're going to show it images, they all have to be the same size. They all have to have the same sort of span in colors or darkness. So you have to make everything uniform. You can improve the performance of your network by showing it different views of the same image, like rotating your image, or adding noise to your image. So just showing it different ways of looking at the same thing. Basically, in computer science, the more training, the better. That's the general rule right now. The more training data you can show it, the better it will perform. So a hidden layer, this is just, as I said, no equations, but here is roughly what a hidden layer is doing. It's very straightforward. You take your image, here again, a cat. Hidden layer is very basic. This is not the cutting edge stuff. Convolutional layers are the cutting edge. But you would take your image and turn it back into a 1-dimensional vector, getting rid of all the spatial information in your image. So that's that vector there, the white one. And then you would multiply it by a matrix. This is that thing there is your neuron. It's one of the neurons. You multiply it by this matrix, and you add this other vector, which is known as the bias. These are called the weights, and that's a bias. And these numbers in there, you don't know to start with. The machine doesn't know to start with. The machine just puts random numbers in there to start with. So all of these have got random numbers in them. So what you end up with is you input an image, you multiply by a matrix, you add this vector, and you get a vector out. Also, what it does is it does that, in this case, this is the neuron that I'm talking about here. It's taking input from one of the images, doing this process to it. What it actually does is does that for all of the images from the previous layer, the input layer, and averages the result at the end. So all you need to think about right now is it's doing this quite simple linear process to your data. And it's got weights and biases. This is exactly the same thing, but for a convolutional layer. Convolutional layer is a little bit more complicated, but quicker to compute, it turns out. Instead of doing this matrix multiplication, it simply takes this you see this little, well, let's look at the yellow one. That's a small image, right? That has got pixels in it, each with a number in it. That's your weights. So it's just made an image. You could have made this into an image, right? With each of these being the brightness. So this is just another filter of weights. And instead of multiplying it by your input image, you simply convolve this with your image. So in here, if you take this yellow thing and you convolve it with this image, you end up with a new image, and it's kind of detected everything that had this kind of shape in it. This is like an edge detection filter. It's going to pick up things that are diagonal like that. And you can see what it does that there. So with a convolutional filter, the idea is you put an image in, you don't flatten it, you get an image out. So it's just changing your image. And it's doing this, each of these neurons will be doing a different filter. This plot is, this is a representation of the 8 different neurons that you would have possibly in this convolutional layer. Okay. This is just a minor thing that happens once you've done that convolutional layer. You can do this thing called max pooling, where if this was the output of your layer, some numbers, you just do this thing where you take small groups of the pixels or the numbers, and you find the maximum, and you write that down. So it's a data reduction technique at the end of each layer that you just slim down your data. And they found that this is a very good way to preserve the information while slimming down how many free parameters you have in your system. It doesn't preserve all the information, it just preserves the key information. So it's like taking an image and then lowering the resolution of that image. So if you have an image of a cat, it's high resolution, you downscale, it's still an image of a cat. That's the general idea. And they found that this makes the thing easier to train and converge to the final answer quicker by throwing away this information that is less important. So I just wanted to throw this in because you'll see this if you try this. If I make you excited enough about deep learning that you go ahead and try this stuff. One of the most important parts of these deep networks is what you do after that stage, after each of these neurons, right? So imagine a convolutional layer has output this new image, and then you've just downsampled it with the max pooling, so you've still got an image. Then every one of the pixels in the image could have any value. And there's this thing called an activation function, where you pass the input, the pixel value in that image, through this activation function, and it remaps it onto a scale between 0 and 1. And it does it with one of these nonlinear functions. And you have lots of free choice. There's these hyperbolic tangents, logistic sigmoids, linear filters, heavisides, and there's inverse tangents as well that aren't listed on there. But basically, it takes the output and remaps that output back to a number between 0 and 1, ready for the next layer. So it's renormalizing everything. So it's just keeping the flow of information sort of consistent as it goes through this network. And finally, a regression layer. And this is where you can have two different types of layers, whether you want to do logistic regression or linear regression, whether you want to do classification or whether you want to do parameter estimation. And I won't go too much into this because this is the bit I find the hardest to understand and explain. But basically, if you were doing classification and you were trying to classify between cats and dogs, what this process does is output into each of these a probability, a number between 0 and 1, and the sum of these two probabilities is 1. So it's just mapping your final outputs from your final layers such that you get a number between 0 and 1 in each of these, and they sum up to 1 like they should do, like for a probability when there are 2 options, or n options. Okay, so that's how a network is structured and what happens inside the network. But as I've said, all of those filters, the weights and biases, I haven't told you how they're computed. So what you have to set up is this thing called a loss function, which is just saying, setting a function up over the parameter space such that at its minimum, it is where you want to be. It is where it's classifying the best. And so you can do things like have least squares error, or log likelihood functions. So because I said in the classification you output an actual probability number, then you can just easily work out the log likelihood. It's the log of that probability. So there is this function, and because when you're inputting the data, you know what the answer is. When you input a picture of a cat, you know it's a cat during the training. When it filters all the way through to the end, and it puts it in the dog box, right? Then you can tell it that's wrong. That's a bad probability, and you can feed back information to this through this loss function. So it's trying to find the location where it's getting more and more of the classification correct. How does it actually now do this process when you're doing the training? It's a stochastic thing. Let's see if this algorithm works, this animation works. So imagine you've got surface. Now in this case it's a 2-dimensional surface, but if you counted how many free parameters you're going to have in this, all those weights and biases, there's hundreds if not thousands of free parameters in this model. But this is just a representation in 2 dimensions. And this is just saying how different types of gradient descent algorithms try and find the minimum of this function. And in fact, this algorithm is made to show that stochastic gradient descent isn't very good, but that's the main thing that's used, is this thing called stochastic gradient descent. it basically is trying random noisy jumps all over the parameter space, just like a Monte Carlo would do, to try and find if it gets better and better and works its way down into the minimum of the loss function. And there's technical things where the only way it can do this efficiently is if all of the functions, if your loss function and your activation functions are all analytically differentiable. That's important. You can't just make any old activation function. It has to be analytic and differentiable, because that's how they do this incredibly quick it's a thing called back propagation, which I won't go into, but that's how they explore the parameter space and are able to change the location of all these pins simultaneously as it trains. If you wanted to do this, and you may not want after hearing what I've just said about it all, it is quite straightforward. There are lots and lots of packages available for you that you don't have to write, right? All you have to do is design the structure of your network and tell these packages, I want 3 layers, I want it to have this many neurons, and this is the input data that I'm going to give, and this is the output classifications I want, and then you press go. And it does all the magic on your GPU and outputs you your result. They work. They will all work, but you will be very much behind anybody that has a GPU. Even the GPU on my old Mac laptop was like 100 times faster than the CPU on that laptop. So even just a Mac laptop GPU was blowing everything up. Sorry? It's because it's highly parallelized. And this is something that these people have done, the computer scientists have done. The most sort of the big names here are Caffe and TensorFlow and Theano. And a lot of these other packages are built on top of those 3, and they're just at different levels. If you wanted to be very low level, you would go with Theano. You can code it all up yourself from the very bottom. We went with that first, not knowing that, and found that it was quite hard. We're now working with Caffe, which is a lot higher level, and it's easier to deal with to design things. Yep. Theano's in Python. Caffe has a Python interface. I don't know about the other things. Some of them, like is digits on there? There's a lot of them that some of them are point and click. You drag and you design your network. So, and they're all, the engine underneath all of these are basically, they're different engines, but they're all about the same speed. So there's no, it's which one you prefer rather than which one you think is fastest, and I think. So the process you would do is you would make your data. Generally, the idea is you break it up into three sets. You would have a training set, a validation set, and a test set. So the training set is what it's doing to sort of update its internal workings. Every so often, it checks how it would perform on the validation set. There's a very good chance, if your data set is small, that it would have excellent results. If you showed it 3 pictures of cats and 3 pictures of dogs, it's going to do very well on those. Right? It's going to be able to identify them accurately, but if you then show it a validation set, it may get that completely wrong because you haven't trained it very well, but it says it does very well on its training set, and that's called overfitting. And so you have this validation set to give you this indication of how much it's overfitting to the data. It's like having, if you're trying to fit a line through some data in 2D and you try and fit it with a 20-dimensional polynomial, it'll fit it exactly. But then if you show it some new data, it'll be completely wrong. So that's what I mean by overfitting. So you have this validation set, and then once you've test-trained your data and you've locked down your network, you said it's now trained, you then would run it on your testing data to give your final accuracy results. How well does it perform on a completely independent set of data that I generated? So that's the way you can be as unbiased and fair as you can with saying how accurate your algorithm is. Then, as I said, you design the structure of your network, and that structure can be applied with any of these pipelines. So then choose your software, which ones you want to use. And then you would initiate training, and that just allows each of the pipelines to decide what those weights and biases are in each of those neurons. And then, as I say, run on your test data and estimate your accuracy. So, how am I doing for time? Got an hour and a half. Oh, that's all right. That's good. So, I will now talk about what has been done. One particular thing that has been done in gravitational waves in the last year by these authors, George and Huerta, who wrote what I think is an excellent paper. No, actually, I don't think it's an excellent paper. I think it's excellent work. I think it's not a particularly good paper. But it's excellent work. So if they see this video, it's excellent work. But it is not particularly clear. But it's very hard to make these new things clear, especially when they're coming from an entirely different field, right? So, let me work. Just now you have a rough idea of what a neural network is and what it's supposed to do. We will forget about exactly that stuff. I'll just talk about what they trained and why they were training and roughly how they did it. So they specified that they were going to work on a binary black hole data set, which is a hot topic right now. That's the things we're detecting, binary black holes. And they were primarily looking at classification, so classifying whether there is a signal in the data or not or noise in the data. And they broke up the data into 1 second segments. So they were making 1 second long segments sampled at 8 kilohertz. So there's 8,192 time samples. It's a one-dimensional data set. It's not an image. It's just numbers in a line. And they dealt with single detector data. So they're simulating this just for a single gravitational wave detector, which is perfectly reasonable when you're doing this for the very first time to sort of estimate whether this even works for gravitational waves. This is their mass map. So you've got mass 1 and mass 2 for the component masses they're simulating. And they did it on this sort of grid-like structure. And if you notice, their training data is more spread out than their testing data. This is a subtle point, which I'll sort of address at the end, but what they trained on, what they tested on were actually slightly different data sets, or drawn from different parameter spaces. This is the two plots from their paper, and they use the argument that they're going to use time series data, this stuff here, and not use time frequency data, because you have this free choice. I can make time frequency data. I can make a spectrogram. This is the same data, right? And you've seen the binary black hole detections, GW150914, where you get a swooping, like where you see the signal, right, in time frequency. You don't see it here. And they argue because you don't see it here, the machine is not going to be able to see it. But they argue that you can see it here. And you can't see it here either. They plot the signal in red over the top, and you can see that. But that's because they plotted it on top. You can't see the signal in here. So they made this spurious argument to start with that they're going to use time series data, but I agree with that choice. It seems to work better in practice than using the spectrograms. Exactly. Exactly. They could have had different frequency and time resolution. They could have done smoothing. That's the other thing. You're not bound to these strict rules for data analysis now. If you did smoothing and then did a Bayesian analysis, you have to account for the correlations between the pixels that you've just smoothed. Here, no. They could have done anything they want to this, and they could have made the thing appear. Yeah. But, well, you see, that I know there is, but it's not clear whether such an optimal choice would be optimal for the machine. All the rules go out the window with these things. It's not clear. It's all trial and error what you show these machines and how well it performs. But that was where I'd start, right? You choose what you think is the optimal to start with. But when you learn that one way to make the machine better is to add noise to this, that is counterintuitive, right? Yeah, it's all, whilst you may not agree that I've explained things simply this morning, it really is quite simple operations that are happening inside the network. It's just that there are many layers of them. And it's just interesting that it is so simple, the operations, but it does get quite complicated when you add these non-linearities into the mix. Anyway, this is the data set. This is a typical data set that they showed the machine. They didn't show this image. They just showed the time series information. And for those who are interested, this is whitened data as well. So they've whitened the spectrum so that the noise is white. Yes, yeah. And they whiten the signal as well, obviously. Now, this is a rather sort of dry slide. It's just saying what they used for their network. And this plot is a plot from their paper, or a table from their paper describing what they did. And this is a plot, nothing to do with their paper, that I've put in to kind of show generally what happens in these networks when they're a bit more complicated than the one that I've shown you before. They've got multiple layers, and if you notice the size of these layers, it puts the size of the images that are coming in and out, not the images, the time series that are coming in and out. They gradually get smaller and smaller and smaller because of this process of convolving and then downsampling, doing the max pooling. And it keeps, you want your data sort of to converge to having more condensed information in it towards the end as it goes through the filters. And it ends up having 1, 2, 3 convolutional layers. So it's convolved with some filter to generate an image from the input image, and then that goes onto the next layer where you have another filter which convolves with that image, which goes onto another one and convolves with that image. Once it's gone through 3 of those convolutional layers, they throw in what they call here a linear layer, which is a hidden layer, the thing I did before, where they take the final image that they had out of 3 and they flatten it into a vector and then throw it into just a hidden layer, and then they have this output layer as well where it outputs into noise or signal, right? And the number of neurons they have, they seem quite small, really. 16, 32, and 64 neurons in the convolutional layer, and then it jumps up to nearly 8,000 neurons in their final hidden layer, and then down to 64, and then down to 2 again. In fact, there's 2 of these hidden layers. I forgot there's 2 hidden layers at the end. And so this is not to do with their analysis, but you can see the general scaling of an image that goes in, and it gradually gets smaller and smaller until it goes to the output. But we're not dealing with images, we're dealing with time series. And there's the results. And unfortunately for them, they decided to qualify, to define their sensitivity in a quantity that nobody in gravitational waves uses, which made it very difficult for people to take them seriously. This is the SNR that Sathya defined before. This is the integrated SNR. Squared SNR is this integral in the frequency domain over your signal divided by your noise spectral density. In this paper, for good reason, I think, they defined a different SNR, SNR peak, as equal to the max of the square root of this, something like this actually, but it was basically the peak in your whitened time series. How high does your signal get compared to the background noise, which doesn't take into account any of the information in the previous part of the waveform. It's just the peak. And it turns out, if you do some simulations, which I did the other day, you can convert, so for those who are interested in real SNRs, you can convert this number, any number on this axis here, by multiplying by 12. They claim sensitivity at SNR 0.5, basically. This is where it starts to drop off. You're getting nearly 99% accurate predictions when their SNR is about 6. This is in Gaussian noise. And this, when you say it like that, is actually quite impressive. especially when you consider this is an all-parameter space search. It's all mass. It's searching all masses, and it's searching all times as well, and all phases, and all for a fixed SNR, for that given SNR. And I'll show you another plot in a second to put this in context again. They also did parameter estimation on the masses at the same time. So remember, that's just the change in that final layer. You either have a logistic layer or a regression layer, and they just switched out the layers, and they ran it again and predicted the masses. And at this particular, as a function of SNR, they get down to this error of around 10% on the individual component masses. If you then go and look at GW150914 and the errors that came out of the individual masses for that analysis at SNR 26, that was 10 to 15%. SNR 26 in these units is around, it was multiplied by 12, so it's around here. This is around 10 to 15%. So it's not the most accurate comparison, but they're getting similar estimates. Now the problem is, with this paper, is that they didn't actually try and make these comparisons. It would have done them a lot of good had they made these comparisons and used the right SNR here. I should also mention this paper, which is an independent paper. For those of you who haven't heard about Gravity Spy, I won't go into the details about Gravity Spy, other than this is a citizen science project where people at home on the internet are asked to, it's like a Galaxy Zoo type project. You're asked to identify glitches from LIGO data, and it helps the LIGO scientists classify the different types of artificial detector glitches. This is not signals, this is glitches. And they wrote very briefly at the end of their paper on this that, oh, by the way, we also applied a deep neural network to this. And these are the results from their deep neural network, which is equally as complicated as the previous one. Except they have about 15 different classes of glitch, which were pre-identified by people at their computers at home. So these people are very smart. They had a data set that was not pre-labeled, right? It's coming out of LIGO, and it's not labeled. LIGO's not telling you what type of glitch it is. They then farm it off to thousands of people at home for free and have them identify all the glitches. And then they take that data now labeled, and they run it through their deep learning algorithm on new data. Well, they train on that data, and then they show it some new data, and they get these accuracies. They're getting like 100%. This is a sort of error matrix box where you can see along the diagonal is when it identified each of the types of glitches accurately. Yeah, they got the right accuracy. And when you have off diagonal, it's when it's misidentified an extremely loud one for a low frequency burst and so on. This is a very diagonal plot, meaning that the machine learning is doing incredibly well. Now, it's hard to gauge how well that is without comparing it to previous work, and I don't have the numbers to hand, but it is a lot better than previous glitch identification algorithms. Yeah, so what's happened is the people, the detector characterization people have gone through initially and identified this subset of possible glitches, but then they haven't gone through all of them. Then they've sent them all out to people at home to do the identification on thousands and thousands of them. So they get labeled sets, and then they throw it into the machine. So you're assuming in this case that the people at home identified them correctly, but they're kind of like a machine as well, and they could have got it wrong. Yeah, they do have validation. Okay. And this, I just wanted to throw in some work from my two summer students, Michael Williams and Fergus Hayes, who have been trying to reproduce the work of the first paper, except trying to put it in context with the performance of matched filtering searches, the ones we actually do. Now, this is very preliminary. I just got this morning. These are ROC curves. For those people who are not familiar with ROC curves, what you're plotting is false alarm probability versus true alarm probability, which is, so up here is where you are correctly identifying signals that you've injected, and down here is where you are misidentifying noise as signals, false alarms. Each of these curves represents a different data set, The brown curve is for SNR, integrated SNR6, this SNR. The orange curve is for SNR8, then there's a blue curve. We don't have enough data yet. It's just a summer project. But you want a curve that goes up and to the left, which implies a good algorithm. These curves actually represent the results you would get from a match filter analysis. So at SNR6, a match filter analysis will be able to identify correctly 60% of the time while allowing a 10% false alarm rate. So you can just read off from each of these curves. The points in the same color are what we've managed to get the